Here VL of t is nothing but VL of t is L into dA of t by dt. Vc of t is, so let me write this equation, rewrite this equation. V minus R into y of t, so it is R into y of t. VL of t is L into the current flowing through that inductor is I of t, so I of t by dt minus this one 1 by c integral minus infinity to t I of t dt is equal to 0. So if I rewrite this equation, V is equal to R into I of t plus L into dA of t by dt plus 1 by c into, split this integral from minus infinity to 0 I of t dt plus integral 0 to t I of t dt, that is equal to 0 here. Now this 1 by c into minus infinity to 0 I of t dt is nothing but initial voltage of this capacitor, so that is V0. So let me rewrite this equation here. So it is not equal to 0, V equal to this one. So V is equal to R into I of t plus L into dA of t by dt plus this V0 is, anyway it is 0, initial voltage is 0, so 1 by c into integral 0 to t I of t dt. Now I need to find this I of t here. For that, what I am doing here is, I am doing again, once again, I'm going to differentiate this equation here. So if I differentiate this V, it is a constant voltage, so that is equal to R into di of t by dt plus L into d square I of t by dt square plus 1 by c. If I differentiate, this integration will integration and differentiation will get cancelled here, so 1 by c into I of t, that is equal to 0 here itself. Now this equation, if I take L as a common here, so d square I of t by dt square plus R by L into di of t by dt plus 1 by LC into I of t is equal to 0. So this equation I can rewrite like this: d square plus R by L into d plus 1 by LC into I is equal to 0. So to find the solution for this equation, d square plus R by L into d plus 1 by LC into I is equal to 0. This is the equation that I got here from this. So here, to find out this I of t, so it is like here it is a second order differential equation. It will have the two roots d1 comma d2. So okay, let us for this let us apply the Laplace transform for this. If I apply the Laplace transform, in place of d we can write as s square plus R by L into s plus 1 by LC is equal to 0. Here this is called as the characteristic equation. So let us assume it is equation 1. It is called as characteristic equation, and it is having the two roots here, s1 and s2. Since it is a second order equation, it is having two roots here. So I am going to find the two roots here. S1 is s is equal to roots minus b plus or minus square root of b square minus 4ac by 2a. So s is equal to b here is minus R by L plus or minus square root of b square is R by L whole square minus 4 into a value is 1 and c value is 1 by LC divided by 2. So here it is minus r by 2l plus or minus 1 by 2 into integral. I can write like this: r square by l square minus 4 by LC. Roots for this. Now it is minus r by 2l plus or minus, if I bring this 2 into the root, it will become 4. So I can write this one as r square by 4l square minus 1 by LC. This is equal to minus r by 2l plus or minus square root of r by 2l whole square minus 1 by root LC whole square. So these are the roots here. So this is let us assume alpha is equal to r by 2l and omega naught, you know that it is 1 by root LC, and also this will become like this: s is equal to minus alpha plus or minus square root of alpha square minus omega naught square, and here beta is equal to, let us assume, square root of alpha square minus omega naught square. So these roots we can write as minus alpha plus or minus beta. So here two roots are there, that is s1 is equal to minus alpha plus beta, s2 is equal to minus alpha minus beta. So the solution for this one, we can write as I of t is equal to k1 into e power s1t plus k2 into e power s2t. Okay, and the values of k1 and k2 we can find out from the initial conditions. And also you see here this depending upon the values of this alpha and omega, we will get three cases here. Those three cases are, let me explain. Case number 1. Before going to explain these cases, first let me explain the S-plane roots. S-plane, let us consider this is an S-plane and it is called as real axis. It is positive real axis, it is negative real axis, it is positive imaginary axis, negative imaginary axis. Here all the negative values of negative real values, positive real values, like that. And see here depending upon the roots location, the system can be over damped system, under damped system, critically damped system, undamped system. Suppose if the roots of this characteristic equation, this is the characteristic equation of the system, if the roots of that characteristic equation are like this, the location of the roots of the characteristic equation are on imaginary axis, then the system is said to be over damped system. This is over damped system, and the response is over damped response. And these roots actually will come like this, they will come like this, and this root will come like this, and these two roots will get collide here, and one root is going like this, another root is going like this, so it is another root. Okay, now if the roots are located on imaginary axis, then the system is said to be over damped system. If the roots lies between this, that means in this place, the roots are in this place, then this is said to be under damped system. This is said to be under damped system. That means if the roots are in these locations, then this is said to be under damped system. The system is said to be under damped system or under damped response. If the roots lies, if the roots are the two roots are located at one place on the negative real axis, then the system is said to be critically damped system. critically damped system. If the roots are placed like this, then it is said to be over damped system. Sorry, this is not over damped system. It is under damped system. Undamped system. It is said to be, if the roots are located in imaginary axis, then the system is said to be undamped system. If the roots are located like this, then the system is said to be over damped system. So it is undamped system. If the roots are like this, then it is said to be underdamped system. The roots are located at one place at real axis, at negative real axis, then the system is said to be critically damped system. If the roots are like this, then the system is over damped system. Now let us consider these three cases here. Case number 1. If alpha is greater than omega naught, what will happen? Whether it is an underdamped system, undamped system, critically damped system, overdamped system, depending upon the values of alpha and omega naught, we can decide. If alpha is greater than omega naught, alpha is r by 2l is greater than 1 by root LC, then what happens to these roots? Now the roots are s is equal to minus alpha plus or minus root of alpha square minus omega naught square. Here alpha is greater than omega naught. That means one root will be minus alpha plus beta and another root will be minus alpha minus beta. That means these two are real roots only. There is no imaginary part here. Suppose if one root is minus 2, another root is minus 4, they will be located in the negative real axis. That is, if it is minus 2 and it is minus 4, let us assume, then it is 0, minus 2, minus 3, minus 4, like that. That means one root is locating at this place, another root is locating at this place. Then the system is said to be over damped system. So the system is over damped system, and the response for this I of t can also be drawn like this. The response will go like this, and it will come like this and like this. So it is the over damped system response. If you draw this system response, it will be like this. Next, case 2. In this case 2, if alpha is equal to omega naught or r by 2l is equal to 1 by root LC, then what are the values of s is equal to minus alpha plus or minus root of alpha square minus omega naught square. This alpha and omega naught both are same here. That means s is equal to minus alpha. That is, s1 is equal to minus alpha, s2 is equal to minus